Hello. Okay. Hello. Sorry, I'm late. Oh, still, what's going on? Oh, weird. Okay. Good afternoon, Isabella. Hello, Rachel. Hello, Amanda. Hello, Aaliyah. Hello, Melissa. Hello, Lydia. Good afternoon, Ardell. Awesome, awesome, awesome. Okay, and I never even knew that the chat. Oh, good afternoon, Tania. Awesome, awesome. Okay, even though I'm starting late, we are still going to move, or because I'm starting late, we're going to jump fast here. Funny day today. I guess every day is a funny day. I don't even know how to get rid of this chat thing. Okay, hold on. Okay. I'm going to. Okay, we're going to do things in an unusual. There were two items. Okay, there's two items on the agenda. We're going to. Why am I trying to explain this? All right. There's free body diagrams that I keep saying that I want to refresh you on. And I spent the other entire class on the free body diagram thing. That was longer than I intended. I don't want to do that here. So, and good afternoon, Farina. Awesome. Thank you. So you remember I had said that I wanted to refresh you guys on free body diagrams because I think there was like they are super important, and there was an important confusion, I think, going on with them that I really wanted to straighten out before the semester ended. And I attempted to do that in the other section, but I went 2 bananas for a small change in pace. I spent the entire period on it. I don't want to do that with you guys. So what we're going to do is I'm going to sort of ask/require that you watch the video that's posted of the other class discussion on that. I will make that a homework assignment and give points for it somehow. With you guys, what I want to spend more of the time doing, and then they'll have to compensate as well. What I want, and sorry, hello. Okay, sorry. Okay. So what I want to talk about is Doppler effect, or at least, but the Doppler effect is extremely important. It is the huge application or implication of what we were saying about waves at the end of last week. I got very hot and bothered, like excited about this whole notion that the speed of a wave is fixed by and constant relative to the medium of the wave. That is like an enormous point. That's ultimately like the major distinction between wave motion and particle motion. It leads to all sorts of enormous implications, not the least of which is our belief in the Big Bang. I mean, I don't want to get ahead of myself here, but like the whole reason we believe that the universe is expanding, which is already strange to think about. And even as I say it, it's like it takes an enormous self-discipline on my part to not even go down that road and discuss like how weird it is that we think that the universe is expanding, let alone that we think the universe is accelerating in its expansion, which is even weirder, let alone that means if you run the tape back in your mind, I mean, if you actually believe that the universe is perpetually expanding and then you just like run that movie backwards in your mind, you can only come to the conclusion that the universe started as a very, very small point in time and space and then exploded out from that point. That's the notion of the Big Bang. Now, all of this stuff that we believe in really actually comes from our belief in something called the Doppler effect, which has everything to do with how wave speeds work. Okay, so Doppler effect is huge, like in the universe, in its implications. It's also huge in that Professor Wu has already, I believe, spent a ton of time on it with you guys, or will have spent a ton of time. Therefore, as I mentioned last time, one of the problems on your final exam will absolutely be a Doppler effect problem. There won't be any mystery. You'll have a practice exam. Like, it's not a hide the ball thing, but I'm telling you right now, a significant portion of your final exam will be about the Doppler effect. Also, let me just quickly say, as I don't want to get into bogged down into the final exam today, but someone did ask in the other class, so let me just remind you or re-emphasize, The final exam will be formatted just like your midterm. I mean, everything will be more compressed in time, but just like your midterm, it will be a take-home document that you will take home, that will be posted, that you will do in your own way, on your own time, under your own conditions, with the help of the internet, with the help of a practice exam that we will have given you, with the help of your colleagues who will hopefully be helpful. Like, all the same rules apply. Definitely. It will be, and just to be as clear as I can for the moment, that will mean that essentially you'll have, God, sorry, I don't even know how to get rid of this chat thing. Sorry. Okay. Yes. Okay. That will mean, again, I'm sort of rushing here. Sorry, but we will talk about this in more detail, but just because I know we're getting close and someone asked, you won't have as much time to prepare to practice. Like, we will get you a practice exam before you have the actual thing. We will hopefully have a moment or a lab period or something to address questions in the practice exam. We will give you solutions to a large extent to the practice exam. We will promise you also that anything in the practice exam that we don't give you a solution for which we don't give you a solution, anything in the practice exam that we don't explicitly tell you the answer, what that means is that if there is for any question that's on your practice exam that you don't get an answer to it explicitly from us, that means that question will explicitly, definitely, verbatim appear on your actual final exam. Like not even the numbers changed. Okay. So when will we give you the practice exam? It'll be toward Right. Okay. Fair question. I see the question in the chat. That's sort of what I'm trying to get at right now. And I'm sorry to be rushing this and everything, but I know that, right. So there's a question in the direct chat is there an exam date yet? That's sort of what I'm getting to here. Like, precisely speaking, no. Like, everything I'm saying right now is a larger concept that you can take seriously, but the exact minute to minute of it, I'll have to post later. But I can tell you this, working backwards, the actual final exam itself will be posted like essentially the last day of classes or the last Thursday of that week when classes end, right around there. Like, the actual exam, I don't think we'll be able to talk about in class the way we did the midterm, but the actual midterm will be the actual final exam will be posted right around the end of classes, whatever that is. And again, even if you look it up right now, like I can't address all the details right now, but it will be posted right at the end of when classes end, and it will be due back essentially the last day of the final exam period. So what I'm trying to say to everybody, as frantically as I'm saying it, what I'm trying to say is, whatever that whole week or whatever of final exams, when you normally have like final exams scheduled at certain times and stuff, you will have that whole week to do your physics final exam at home, for good or for bad. We will not, whatever day it says that we're supposed to meet to have a final exam in physics, we won't meet that day. You won't be coming in for that. And even if the physics exam is supposed to be somewhere early in the week, it doesn't matter. Your physics final exam will be due essentially the end of the final exam period, and it will be posted essentially right at the beginning of the final exam period, i.e. the end of classes. So basically you'll have a week to do it. And basically you can assume that whenever final exams are over, and I think it's a Thursday, that's essentially when your exam will be due. Again, I will post this more specifically and directly, these details, especially when I post a practice exam, which is not going to be right now, but will be in a week or two, whatever. I know we have very limited time left. Okay. Thank you. Great. Thank you for acknowledging. I totally appreciate it. Okay. So all of these concerns are legitimate, of course. I'm just trying to rush right now because I'm that way. But right. So however, whatever you came to get habituated to in the midterm, it's like that mentality, again, just probably a little bit more compressed in time just because of reality. And I can tell you all right now too, that final exam, and it'll be formatted similarly, like 3 or something large problems divided into many parts. You have to show all your work. You have to make the question clear, just like you did before, all that stuff. I can tell you right now that one of the major problems on the exam will be a Doppler effect problem. I can also tell you that one of the problems, even though we haven't said anything about it in lecture, but one problem will be a circuit problem, because my understanding is that at least by the end, Professor Wu will have done that sort of in detail with you guys. So, and then there will probably be one other problem as yet to be discussed. Okay, so that all of that to be said, it's really be really good to practice and know the Doppler effect. Now, I've started to build up like my conceptual underpinnings of the Doppler effect, but I'm not pretending for a minute that I have walked you through it or anything like that. I have not. I do believe Professor Wu has or will have. But what we're going to do today, and I see there's something in the chat. I'll check out the chat in 1 second. Sorry. In a moment, I'm going to post you, I think, a very detailed packet of notes, like my notes, of how to, a walkthrough of how to solve a Doppler effect problem. Again, I think you'll find it very consistent with what Professor Wu is saying. I mean, I hope it'll match up. I mean, it will match up very directly to what Professor Wu is saying. You will find in my packet of notes that I talk about, I believe there's 4 basic cases you could ever think of in the, oh, someone's here, sorry. I think someone's here. There's 4 basic cases to look at in the Doppler effect. I mean, and I'm saying all this, I know I haven't even said word 1 in this class yet, like literally what the Doppler effect is. I'm holding that, but assuming that you've heard, well, yeah, no, I'm afraid to. This packet will say what it is, will address the fact that there's like 4 standard cases. I mean, if this means anything to you, when I say 4 cases, I mean a receiver approaching a source of, so the Doppler effect is about waves. It particularly comes up, or most commonly comes up in the case of sound waves. Like the Doppler effect is like when you hear a motorcycle go past you on the street and coming towards you, it's and then going away from you, it's like that business. That's the Doppler effect as it manifests through sound waves. Ultimately, it manifests itself in light as well, if and when we believe that light are waves, that light is waves. And so the equivalent to which is what happens with sound, the equivalent in light is that light coming toward us, light coming from something. Wait, I don't even get into that. Sorry, but anyway, the Doppler effect is like really that's what it is, and it can arise in essentially one of 4 basic cases. It arises when a wave is sent from a source to a receiver, but if and when there is either the source or the receiver has any motion at all relative to the medium, right? So if a source just sits in a medium and a receiver just sits in a medium, so if a speaker just sits in air and plays a sound, and that sound is heard or received by a receiver sitting in air, then whatever is sent is heard, and there's like nothing interesting. If everything's just sitting around in the medium, there's just a transmission of a wave, perhaps a sound wave, and nothing interesting, nothing weird happens. But if either the source or the receiver has motion relative to the medium for that wave, so specifically if like a car is going through the air, or a car is sitting while it's like blaring its horn, or a car is sitting still in air, but you are running toward the car or running away from the car while you listen to the sound of the horn coming from the car. In any case like that, if there's any motion at all of either or both of the receiver and source relative to the medium, then the frequency emitted is not the same. Well, excuse me, then the frequency as measured by the source is not the same as the frequency as measured by the receiver. That's the essence of the Doppler effect. And when I say that there's 4 different cases, I mean that just in sort of general terms, you could have a receiver moving toward a source, or you could have a receiver moving away from a source. That's 2 cases. Or you could have a source moving toward a receiver, or you could have a source moving away from the receiver. And in all Doppler effect problems, the premise is some kind of frequency is measured by the source, and some kind of speed is given for either the source or the receiver relative to the medium. And the goal of the Doppler effect problem is to find out what is the frequency of the wave as measured by the receiver. I'm saying this all very spastically, and I apologize. But that's the summary of the Doppler effect, is that if given the frequency of a wave as measured by the source and given some other basic data, then our goal is to find out what the frequency is as measured by the receiver. And that can arise in one of these 4 different permutations. In any of the, oh, someone's in the waiting room, sorry, and thank you for, sorry. In any and all of these 4 cases of the Doppler effect, the way we solve, the procedure for solving is always the same. but the answers we get are different. And when I say that and I do see that there's stuff in the chat, and I will get it in a second, and I am sorry, but when I say the procedure for solving for the received frequency is the same, I mean it's the same as the one that hopefully Professor Wu outlined for you, that I'm not saying you've memorized or that you know cold at this point, but hopefully you have access to and have in your notes, and is the same as a procedure that that's in a lengthy packet of notes that I'm about to give you all and ask you to use. But what it's not, what the procedure is not, is this one equation that you can find on the web that I'm just warning everybody right now. There is a Doppler effect equation on the web that looks very handy and looks very convenient and helpful. And it looks like you just plug in given information, you get out the answer. But if you think I have strong feelings about or against Chegg, triple those feelings about my feelings about this Doppler effect equation on the web. I'm telling you right now that anytime we give you a problem about the Doppler effect, it's designed to make sure that you just don't blindly plug and chug into that equation, because that equation has lots of problems. It really has lots of problems, even though it looks like it doesn't. And so this is one area in physics where we sort of go out of our way to make sure that you actually conceptually understand what we're talking about, and you don't just blindly plug and chug. It won't work, and it'll upset us. So this is a long way of saying, in a minute, I'm going to look in the chat, see what's up in the chat. Then I'm going to give you the posting like pre-notes for this class, like the note. I'm going to give you a whole packet of notes on this. It has a Doppler effect problem in the notes. It even solves it for 2 of the cases. But I want you all to, on your own, use this packet to practice. I want you to solve the Doppler effect problem that's in the notes. So again, it's kind of like a practice exam thing. Like, in fact, if you go through the notes carefully enough, you'll see that I'm even giving you the answers, and I'm even so it's like a sample problem in the textbook. I am walking you through it. You totally can guide yourself via the notes by doing, but you'll know that you're actually accomplishing something and learning something, in that the notes ultimately walk you through, I believe, 2 out of the 4 cases. But to know that you actually know the Doppler effect, you have to be able to solve all 4 cases. And that's what I'm going to ask everybody to do right now during this class period. In a minute, as soon as I get you the notes and as soon as I get the chat, I'm going to ask you all to. So again, maybe you already get this from Wu, in which case, great. This will be nice, easy final exam practice for you. Maybe you don't yet get it from Professor Wu. So then please look at my notes or put them alongside of his and see what you see. And you can help each other and all that stuff. But I'm sort of trying, I don't want to just repeat the same lecture he gave. I think that would be a waste of everybody's time. So give me a sec. So I know I'm being so this is like a hurry up and wait situation. I'm frantically trying to explain something right now so that in a minute, we can all take a breath. And in a minute, you're going to work individually or in groups on solving a Doppler effect problem. So it will be calm in a second. So I apologize, but let me look in the chat. I think oh, I guess I did. Wait, maybe I did answer the chat. Oh, okay. It looks like I did answer the chat. Well, I have no idea. Wait. Okay. Did I just lose? No. Okay. So bear with me for a second. So yeah, so this packet right here that you're seeing on the screen, I'm about to send to you, but I'll flip through it in a second to tell you what I'm talking about. Wow, it's so exciting. Right on the screen, you can see as it's being shared. This is like a moment of sharing. I hate sharing. I'm sorry. I mean, I hate sharing. I like taking turns, but I don't like sharing. Okay, it's and I think they are different. You know, like at the playground, they're always telling, "Oh, yeah." Every parent is always apologizing for the little kid, like, "Oh, Johnny is not." It's like, "Can I ride your bicycle? Can I ride your bicycle?" "Oh, Johnny, come on, share. It's time to share." No, no one's asking you to share your bicycle. You can't put 2 kids on a bicycle. That's ridiculous. Like, we're asking, can we take a turn? Anyway, sorry. Obviously, that's an outside issue of mine. Okay. All right. Okay. I'll probably rename this later for anyone who cares, but okay, so all this like fascinating activity that's happening on the screen means that hopefully what just went to your stream or to your whatever in Google Classroom is a full packet, is this packet, okay? And I'm going to show you right now, like, okay, so there's explanation, there's my handwriting, blah, blah, blah. A lot of it is like a review of exactly what we were, talking about last week. Is just trying to build up and remind you that why the speed of a wave is always relative to its medium. Okay, now here, I'm saying right here, in the case of sound, the speed relative to air at standard temperature and pressure is 340 meters per second. So you can use that as a given in any Doppler effect problem that we give you. I mean, we'll give it to you again, but you can rely on that. But that's the speed of the sound relative to air. Okay, and then blah, blah, blah. I'm flipping this. So this is a lot of this is hopefully review or reminders of things you know. This just now relates waves to sound waves in particular. The reason I'm flipping these pages, okay. Well, this is what I was saying a second ago very frantically. Like, this is your basic situation, your basic Doppler effect situation. It looks like, and again, this is where Professor Wu is much better at drawing these things and stuff, as I'm sure you've seen. But the basic situation is you have a source, which in the case of sound, you could think of as a speaker. You have a receiver, which in the case of sound, you could think of as like an ear, right? And then you have a wave that's going from the source to the receiver. What's always given in Doppler effect problems is the things in red. The velocity of the wave relative to the medium. So in our case here, that would be like the velocity of sound relative to air is given as 340. What will also be given are these other two things in red, the velocity of the source relative to the medium. Like, is the speaker moving through the air or not? In 2 out of 4 Doppler cases, it is. And then similarly, velocity of receiver relative to medium is given always. Let me also back up and say again, I mean, it says it somewhere in this packet in prior pages, but like S stands for source, R stands for receiver, M stands for medium, W stands for wave, okay? The other two things that are given always in the Doppler effect problem are the frequency of the wave as measured by the source, that's FWS I have up there in red. And what you're always solving for in the end is what's the frequency received. Now in English, by the way, again, I hate to drag this out, but this whole concept of the Doppler effect applies to any wave you can imagine. But it's very common and familiar and vivid and interesting when it applies to sound. In the case of a sound wave, the frequency of the sound wave is what the human brain registers as pitch or note, like where, like how high or low it is in, not in volume, but in pitch. Like whether, so like, for example, if the note, if sound vibrates at 440 cycles per second, 440 hertz, as it says earlier in this packet, that's what the human brain registers as the middle A of a piano, like literally the A note that's in the middle of a piano keyboard, not the middle C, the middle A. I mean, there's also something called middle C, and that's 256 hertz, but 440 hertz is a middle A. And in other words, frequency is how high or low it sounds to our brain. So what we literally are saying in the Doppler effect here is you can play one note out of the horn of your car, but if your car is moving toward someone while it plays, then that person will hear a different note. Like, that's what we're saying. And you're here to solve for the note that is heard rather than the note that's played. And they will differ as long as there's any motion at all of either the source or the receiver relative to the medium. Why? That's what you figure out while you're doing it. Well, you'll see while you're doing it. But anyway, so this is all the setup. The problem that you're going to do right here, okay, like right here on page 25 is the case that I'd like you to do. Now, it actually will solve this case for you in the packet. So I'm not like leaving you high and dry, but I think if you're trying to practice for the final exam, like, don't even look any further in the packet. Just try to solve this. Here's the givens. Assume it's sound moving at a speed of 340 meters per second relative to air. Assume the source, the speaker, is just sitting there, still in the air. Assume that the frequency of this note that's being played is a 440 hertz. So that's middle A, if you care, if you can relate to what that means. And assume that the person listening to the note is coming toward the source of the sound, is approaching, receiver approach, it says, at 40 meters per second. So I've even sort of given you a hint and called that negative. Like in general, what we, anyway, I'm giving you a hint saying you should, the speed, I'm just telling you, the absolute value is just 40. But if you set things up so that the direction of the wave is what you call positive, then if the receiver is coming into the wave, you would say that the velocity of the receiver is negative. Like that's in the problem, that's a hint. Those are the givens. You're there to solve for F sub WR. That's your goal. Again, if you get stuck or whatever, you can flip it in the packet and it'll show you how. But what I really want you to see once you're looking at the packet is that there's 4 different cases. It could be receiver approaching or receiver going away. It could be source approaching or source going away. Once you flip through the packet and see how to do one case, it is exactly the same procedure for all 4 cases, but you will get different answers. Okay, so what I'm asking everybody to do now, I know now we have like 50 minutes left roughly. Yeah, we've like a little under an hour. I'm asking you to start by solving the problem right here on page 25. And then if you think you're confident and you get it, then move on and keep the same exact numbers, but just change the situation to having the source move, or change the situation that's having the source moving away. And make sure that you're versatile and skilled enough to be able to do all 4 cases. Again, if you don't feel that versatile or skilled yet, just keep reading through the packet and seeing what's what. Okay, I'm saying all that. That's the goal for right now, for today. Could I get any kind of, oh, funny, I didn't even see our, yeah, good, thank you. I'm actually glad I got some response to that. Yeah, no, I hate you. Oh God, Sharon. And it's not like I don't have, anyway, so thank you. But now, assuming actually everybody hates, like part of me really wants to put you all in breakout rooms and blah, 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 but yeah, actually I am. I'm going to put you in breakout rooms so that you have the benefit of each other's colleagues. But I'm going to tell you right now too, well, as soon as I can get a confirmation that this is sort of clear what I'm asking, like the Doppler effect might not be clear, but as long as the task is clear, what I'm going to do is I am going to put you guys in breakout rooms, but I'm telling you right now that you're on your own in a real way. So even if you just end up walking away and doing it on your own, I'm not going to know, and I'm not going to enforce. I'm also not going to help particularly. So I'm going to put you in breakout rooms and leave the Zoom room, and leave this on so that anybody who actually wants to make use of this time in a synchronous way totally can. But if you walk away and do it on your own, I won't know, I won't yell, but you are responsible for this work, obviously, and it's totally to your benefit on the final exam and all that. But also I'm not going to be in a breakout room. So when class is over, it's probably just going to end. I'll try to regather us, but I'm also going to try not, because I'm very worried that if I regather us, then I'm going to start babbling again for way too much time. So like once I say go, we're going to go onto this problem and in whatever mental state works for everybody. So can I just get any kind of confirmation or like as long as, wait, I'm going to turn off this chat thing here. It keeps coming here. If I can just get any kind of confirmation that you understand. Okay. Thank you, Arno. That's good enough for me. Okay. Thank you, Lydia. Thank you, Isabella. Okay. All right. So I'm going to, 1 second, I'm going to assign the breakout rooms so that you have them, but do what you want with that. I mean, for that matter, I could just, well, yeah, no, that's what I'm going to do. Hold on. But they're not. Okay, so the rooms are open. Please do go to one, just like go to one for a moment. Yeah, do me that favor. Everybody go to one at least. Let me see that everybody's gone to one. But then once you get there and you say hello to your peeps, if you then need to go or something, that's your business. But just work it out with your colleagues so that no one's actually being totally obnoxious. And then you won't have to recheck in with me at the end. Like we're just adults from here on. Okay. Well, once I see that everybody's gone, I will be happy. Okay, so like, great, thank you. So Farina, you're good? Great, thank you. Okay. Arlene, you're good? Do you hear me? Are you there? So please go to breakout rooms. Hi, Billy. Go to a breakout room, please. They'll explain when you get there. Good to see you. Thanks.